Now we've demonstrated how to convert a number from a certain base to decimal. What about if we want to go the other way? So let's say we've got the number 114 and we want to convert that to base 2. Now, what's the base 2 representation of this? So this is a different process. This one we're going to work with the quotient. So we're going to divide and get the quotient, and we're going to use the modulus. And so we're going to keep track of several things as we go through this loop. And by the way, this algorithm is, well, it's written in the textbook, but it's incomplete. So let me get that. So the algorithm from the textbook has limitations, right? And so we're working with the base where base is greater than 1 and n is greater than or equal to 1. And then here's the real limitation. The output of this is that the digits are output in reverse order. So if you were going to implement this in a computer program, you would need to be able to store those digits and print them out in reverse order. Here, they're just outputting them in the backwards order, which is not satisfactory. So this is incomplete because the ordering is there. But let's go ahead and we'll remember that ordering issue, and we'll write it in the correct order when we get done, okay? So these are the things we're going to need. We're going to need x, which is the number we're working with. We're going to need the base, and so we're going to keep track of what the base is. We're going to need the quotient, right? That's this x div b, that's the quotient. And we're going to need the remainder. So I'm going to line it up like that because that will keep things nicely in order. And we'll start with x as the 114. Now the base is going to be 2, and that's going to be consistent throughout the entire loop. As we do this, b never changes. It's always base 2 is what we're converting it to. And what we're going to do is we're going to compute the quotient and the remainder, and that's going to be valuable. So 114 divided by 2, let's see. So we can do this with a calculator, or we can do it in our head, whichever works better. 114 divided by 2 is 57, and then the remainder is what? If we go back there, notice this divided evenly, so the remainder is 0. Now when we're working, remember that remainders are going to be in the range to 0 to 1 less than the divisor, right? In this case, the base. So it's going to match exactly with the digits that are allowed, because that remainder is always going to be in the range that the digits are allowed. Nice match. All right. So once we compute those, then our next iteration through the loop is we move the quotient to x. So we found the remainder there. We move the quotient to x. The base stays the same. And we compute, and we make sure that x is greater than 0. And it is. So x is greater than 0. So we're going to compute the div and the mod. So 57 divided by 2, 57 divided by 2 equals 28. But now there is a remainder, right? So if we take that 28 and we do times 2, then we see that we've used 56. So 57 minus 56 tells us the remainder, which is 1. Now when we're working with binary, this is awesome. There's either a remainder of 0 and 1. Those are the only two options. So these ones we can do in our head, right? So now we have a remainder. So before the x becomes 28, and we test, is x greater than 0? It is, so we're going to keep going. The base stays 2, but now we compute the quotient. So 28 divided by 2 is 14, and the remainder, since that's going in evenly, the remainder is going to be 0. Then we do it again, and x becomes the quotient. The base stays the same. And now we do, what's the quotient? 14 divided by 2 is 7. That divides evenly, so the remainder is 0. We keep going. X is greater than 0, so x becomes x becomes 7. The base is 2. And we do the divide. 2 will go into 7, 3.5, 3 times with a remainder this time, and it's going to be a remainder of 1. 3 times 2 is 6, and take 7 minus 6, and you get 1. And then 3, we move x to, we move quotient to x, which is 3. The base stays the same. We do the division. 3 divided by 2 is 1 with a remainder of 1. Okay, now we're not done. What do? We put x becomes the quotient. So we put that there. It's really easy to stop here when it's 1, and that's one step too soon. So make sure you don't stop yet. The base is 2. You do the division. 1 divided by 2 is 0, right? 2 will not go in, 2 will go into 0, go into 1 0 times with a remainder of 1. And now when we move x, or when we move quotient to x, we get 0. This is where we stop. When x becomes 0, we stop. And then we have the actual answer is in the remainder. And that's where our numbers are in the remainder. Remember, those are the ones that are the digits for that base. And so we write them out, but we write them from the bottom to the top. That's the reverse order. 1, 2, 3, 0, 0, 1, 0. Now this is base 2. This is no longer 10. This is base 2. So we need to be sure and put that subscript on there to identify that. And what we've done here is we have demonstrated that 114 base 10 is equal to 1110010 base 2. So we've done the conversion from decimal to binary.